In 1988, the world was given its first sight of the United States' top-secret stealth fighter, the Lockheed F-117. And a year later, Northrop lifted the veil from its B-2 bomber. Even before this, the Lockheed SR-71 Blackbird strategic reconnaissance aircraft had demonstrated a number of novel features designed to make it as nearly invisible as possible to enemy radar. The idea of invisibility is not new, of course, and has been a popular subject in fiction for centuries. It was thus inevitable that as soon as the military possibilities of the airplane began to be seen in the early years of the 20th century, people would begin to think of ways of making this new weapon indetectable by the enemy. In fact, as early as 1912, one Austro-Hungarian officer covered his aircraft with transparent film so that at an altitude of 1,000 feet, all that could be seen were the engine and pilot, making a tiny target. But as aircraft became both larger and faster, with more engine, more crew members, and more weapons, different methods of concealing them had to be devised. At the same time, of course, other scientists were working on ways of detecting them. One of the biggest problems in concealing an aircraft has always been the noise it makes. While early planes were small and underpowered, with engines making little more noise than a lawnmower, a modern jet fighter is a noisy beast indeed. When it is flying at supersonic speed, of course, there is no audible warning of its approach, but it still lays a footprint of sound behind it to enable enemy observers to plot its course and make a good guess at its target. At subsonic speeds, this footprint is less easy to track. But on the other hand, the aircraft advertises its presence before it arrives. So, sound detection has been an important method of tracking enemy aircraft since the earliest days, and reducing the sound signature, an equally important aim of aircraft designers. Early aircraft were as small as they were quiet, and from a distance could easily be mistaken for birds. This is hardly true of a modern multi-engine jet, such as this United States Air Force KC-10 tanker. Painted like this, such an aircraft can be seen for miles, either from the ground or from another aircraft. So, most modern military aircraft are painted in camouflage colors like these C-141 and C-5B transports. The paint scheme, somber Europe 1 camouflage in this case, is dull brown and green on the upper surfaces to help the aircraft blend into the landscape when seen from above. And a pale blue or gray on the undersurfaces to make them less easy to spot from the ground. Unfortunately, we cannot yet emulate the chameleon and change the camouflage to suit the background at a moment's notice, so even camouflaged aircraft often stand out like sore thumbs. With this in mind, once the British task force was at sea in 1982, headed for the South Atlantic to recover the Falkland Islands from Argentine occupation, the Harriers and Sea Harriers aboard the carriers Hermes and Invincible were hastily repainted. The whites were painted out of the roundels. Identifying lettering was covered over, and the remainder of the aircraft, including underwing stores, was camouflaged a dull gray to blend in with the wintry sea and sky. No matter how cleverly aircraft are camouflaged to merge with their surroundings, their pilots still have to communicate with each other, and on occasion, with ground control. These T-38 trainers, dogfighting with F-15 Eagles and F-5E Tiger IIs over Nellis Air Force Base near Las Vegas, are mainly painted in low-visibility gray to match most backgrounds. But there's still a lot of radio chatter which would give their positions away to a real enemy.
Are you going to gunfight? Well, good. Okay, I'll call you home, Jeff. Bandit, you're 6. Eagle 2, engaging the F5, coming off Eagle 1. Snapshot F5, right-hand turn.
Radio and radar waves fall at the top end of the electromagnetic spectrum, and together with infrared, occupy a broad band which is the chief concern of a stealth aircraft designer. Visible light, each color having its own wavelength, fills a comparatively tiny band. Below this spectrum fall ultraviolet, X-rays, and gamma rays, but these are only marginally important. Infrared or radiant heat is a different matter and of crucial importance. Back in 1949, a team of engineers headed by Dr. W. McLean of the Naval Weapons Center at China Lake began work on a passive infrared homing device which would be small enough to fit into the warhead of a missile. It could then guide the missile straight onto the hot exhaust efflux from a jet engine. This was a major challenge in the days before transistors or microchips, but the research resulted in the world's first true guided air-to-air missile, the Sidewinder. Since then, hundreds of thousands of Sidewinders have been manufactured, first seeing combat in 1958, and subsequently in dozens of wars around the world. The Sidewinder, considerably improved since those early days, is still in service with many nations despite its limitations. Sidewinder is a great weapon in reasonably good weather conditions, but its ability to track targets such as this QF-102 radio-controlled drone falls off in rain or thick cloud. Here, the drone provides a fat, juicy target for the crew of an F-4 Phantom II. An electronic whine from the missile's seeker head telling them when it's locked on to the hot jet pipe. Once launched, the missile heads unerringly to its target, the resulting explosion breaking off a large piece of wing and causing the drone to disintegrate in mid-air. During the Second World War, formations of bombers like these B-17 Flying Fortresses of the American 8th Air Force might number as many as 1,000 aircraft and fill the sky for a distance of 100 miles. In these circumstances, camouflage became pointless, and eventually the bombers were left in factory-fresh natural metal finish. Over the Eastern Front and elsewhere, barrage balloons helped defend cities against low-flying aircraft. While air raid sirens wailed to warn civilians to scurry for shelter, horn-shaped sound detectors would be ranging and plotting the raiders' approach. Fighters would be scrambled to intercept them, and the crews of anti-aircraft guns put on full alert. After a hesitant start, the Russian air defense groups became adept at intercepting the Junkers 88s and other bombers of Hermann Goering's vaunted Luftwaffe. By 1944, the Allies had established almost total air supremacy over Western Europe, and since the bombers had already abandoned camouflage, U.S. high-level escort fighters, such as the North American P-51D Mustang, also began appearing in natural metal finish. This saved a little bit of money for more important things and slightly enhanced performance as well. In contrast, the British Royal Air Force retained camouflage, especially since by this stage of the war, most fighters such as this Mustang were principally engaged in low-level ground attack work. Britain developed the best air defense system in the world during the war. A key element in this was the Royal Observer Corps, who used sound detectors as well as stereoscopic rangefinders to track incoming enemy aircraft, or, as in this case, V-1 flying bombs. It was their job to tell friend from foe, and their simple methods are even today immune to countermeasures by the most advanced technology. Their reports were telephoned to sector centers where plotters could maintain an up-to-the-minute picture of the situation, so that controllers could direct interceptor fighters and ground defenses.
Mike 3-3, direction northwest.
Anti-aircraft gun sights had their own sound detectors, later supplemented by target acquisition and tracking radars, together with rangefinders to control the fusing of the proximity shells and the aiming of the 3.7-inch or 40mm Bofors guns.
15.
Direction northwest. Gun off left.
Over the Pacific and Indian Oceans, formations of Imperial Japanese Navy G4Ms, known as Bettys by the Allies, also proved the vulnerability of the bomber to increasingly sophisticated detection methods. In fact, this particular aircraft was so prone to catching fire when hit that it was nicknamed the One-Shot Lighter. Despite the vast distances over the oceans, the bombers would often give their presence away by an incautious Morse signal over the radio. It was the same the world over. Despite setting out in their carefully applied camouflage, these Italian Cant Z-1007 three-engine bombers could all too often reveal their position by a Morse radio signal, which would alert defending fighters 100 or more miles away. These Savoia Marchetti SM-79 bombers were lucky to make it to the target area. By 1944, the air war had swung almost entirely to the Allied side, and concealment was not only unnecessary, it was virtually impossible. Massed formations of American B-17s and B-24s were escorted into action by droves of long-range Mustangs, Lightnings, and Thunderbolts, whose pilots had a field day against any Luftwaffe fighters which ventured into the air. Still, the Germans persisted in counterattacking, and the contrails from dozens of dogfights filled the skies over Germany, as they had done earlier over England during the Battle of Britain. Even this late, few aircraft were fitted with radar, although some night fighters had airborne interception sets, and the heavy bombers were fitted with contour mapping radar to identify targets at night or through cloud. Most pilots still placed more reliance on the Mark I human eyeball. On the ground, radar had become in many respects one of the most important weapons of the war, and certainly one of the most versatile. Anti-aircraft defenses relied on a dense network of radars operating in different wavelengths. The principle of radar, which is an acronym for radio detection and ranging, is simple to describe, but less easy to make work in practical reality. A radar beam does not exactly bounce back from a metallic object as is often assumed, but sets up a resonance of electric and magnetic currents, and it is these which scatter to form the return signal. Both the size and the design of an aircraft determine its radar cross-section, or RCS. Early radars only operated on a single wavelength, which was specifically selected to give the maximum return signal from an aircraft of specific RCS. Since most bombers were of a fairly standard size, it was possible to rationalize this, and the British system, originally codenamed Home Chain, used the 13-meter band at a frequency of 23 megahertz. The Germans had their equivalent systems, such as Freya for long-range surveillance, and Würzburg and Giant Würzburg for giving precise aiming directions to their sector plotters and controllers. The Allied air forces had great respect for these systems and would attempt to confuse the enemy by making feint or dummy attacks, or by making sudden changes of course, or by a combination of both. Sometimes the enemy would guess wrong, and the intercepting Focke-Wulf 190s and Messerschmitt 109s would take off and head for the wrong place. By the summer of 1943, a new system had been devised to further confuse the German radar operators. As early as 1941, tests had been made with aircraft dropping thousands of strips of aluminum or metallicized paper. Known as window or chaff, these strips were cut to match the wavelength of the defending radars, Each strip, therefore, gave the same reflection as an aircraft, giving the enemy literally millions of apparent targets. Of course, the Germans soon realized what was happening and altered their wavelengths, but it was even easier to modify the length of the strips. One of the most effective uses of window came on D-Day, June the 6th, 1944, when RAF Lancasters and Stirlings flew precision orbits over the English Channel, dropping 12 bundles a minute. On their radar screens, what the Germans saw was an apparent invasion fleet approaching Boulogne at a rate of 8 knots. The RAF also developed a powerful airborne jamming transmitter, codenamed Mandrel. This emitted a band of radar noise to blot out the pulses from German long-range detection equipment. Selected aircraft in each wave of bombers carried this equipment, but left gaps in their coverage because the act of jamming itself reveals the presence of an aircraft, even if not its precise location. The British rapidly became world leaders in what Winston Churchill called the Wizard War, and also developed a system codenamed Moonshine. Using this, a single aircraft could simulate a much larger number. By 1943, airborne interception radar, or AI, was well established. But a problem was encountered when the bombers dropped window, because this also confused the radar in defending fighters. To get round this, the Royal Air Force modified the excellent American SCR-720 helical scan radar. This rapidly replaced all previous airborne interception radars. It had the added virtue of being able to scan a much larger volume of airspace. Fitted with this, blunt-nosed mosquitoes emerged as the best night fighters of the entire war. Naval aircraft also acquired radar as the war progressed. Even elderly Swordfish torpedo bombers were fitted with anti-surface vessel radar, or ASV. The ASV-X, later known as Mark 11, were mounted in a radome under the forward fuselage. It became operational in 1943 and was later fitted to the Barracuda as well. Although designed principally to detect enemy shipping, especially submarines, it was also an invaluable navigation aid. Aircraft so equipped played a vital part in defeating the U-boat menace. After the Second World War, the Soviet Union was quick to develop a wide range of air defense radars. At first, they were based upon American, British, or German designs. But by the 1950s, the Russians had evolved their own technology and had an extensive network of radars to control and direct their growing fleets of jet interceptors and surface-to-air missiles, or SAMs. The PVO Air Defense Organization trained tens of thousands of conscripts to use these increasingly sophisticated radars, which were now of variable frequency to allow them to scan a wide variety of different wavelengths, making them more difficult to confuse or jam. The United States and Britain similarly developed an extensive air defense network. At the heart of this network was the Ballistic Missile Early Warning System, or BMEWS, which covered every possible approach for Soviet missiles over Europe or across the North Pole. For the moment, no one was even thinking about stealth aircraft. By the mid-1970s, the United States had developed the Airborne Warning and Control System, or AWACS, normally carried by the Boeing E-3 Sentry. Inside each E-3, 16 mission specialists, sitting at computerized radar consoles, keep a constant watch and can not only vector fighters onto a hostile target, but also direct friendly bombers and attack aircraft. The very special radar of these aircraft, with a huge 30-foot scanner inside a rotating radome, can detect and track every aerial target within a radius of about 230 miles. For decades now, Western analysts have been saying that although Russian fighters might be fast and agile, in terms of high technology, they were years behind the latest NATO aircraft. It therefore came as a huge shock when observers were able to examine the MiG-29 at close quarters when it made its debut at Farnborough. Here was an aircraft which not only had a superb look-down, shoot-down pulse Doppler radar, but also a goldfish bowl infrared search and track sensor in the nose, a laser gun ranger, and a helmet-mounted sight. The last three features are all absent on such Western fighters as the F-15 Eagle, F-16 Fighting Falcon, and Tornado. An even bigger and more sensitive passive infrared sensor is mounted on the fabulous Sukhoi 27. Using this device, a Soviet pilot can switch off his radar, making him more difficult to detect, and home in on hostile aircraft in fast and deadly manner. The MiG-29 and Sukhoi 27 are both examples of a new breed of silent fighters that need not betray their presence by switching on their radars. In absolute contrast, the American B-52D bomber, seen here in action carpet bombing at medium altitude over Vietnam during Linebacker 2, presented an enormous radar target, as well as emitting huge amounts of heat and noise. At the same time, their various active avionics systems broadcast an enormous variety of radar and radio waves. Stealthy it was not, and American losses to Vietnamese SAMs forced them to modify the later B-52G and H with numerous new electronic defense systems and to operate them at lower level. Even so, they still belch out vast quantities of noise, infrared, and smoke. In fact, the B-52 is almost a perfect example of how not to build a stealth aircraft. Its enormous engine intakes and pylons, coupled with the slab-sided fuselage, huge vertical tail, and predominantly straight lines, make it a perfect radar target. No amount of new internal equipment can compensate for these defects, but it must be remembered that the B-52 was designed and built at a time when few people had really begun thinking about stealth concepts. To make the surviving B-52s less vulnerable, in the strategic role, they are now equipped to carry AGM-86B air-launched cruise missiles. They can launch these from a distance of some 1,500 miles without coming within range of enemy fighters or missiles. Even while the B-52 was entering service in the mid-1950s, designers were beginning work on a replacement, although it took 22 years before the Rockwell B-1A first flew. It was very much a product of 1960s thinking, with the emphasis on a high-altitude speed in excess of Mach 2. Even so, enough thought had gone into its design that its radar cross-section was only 1/10 that of the B-52. 4 prototypes were built, but President Jimmy Carter canceled the program despite the fact that the aircraft greatly exceeded its design parameters. His decision was influenced by the fact that by the late 1970s, the emphasis had switched to low-level attack, and normally at subsonic speed. Nevertheless, Rockwell continued to work on the B-1, adapting it to incorporate some features from the F-117 stealth fighter program. And when Ronald Reagan became president, he authorized the much-improved B-1B into production. Although superficially similar in appearance, the B-1B Lancer is in fact a very different airplane. It still has variable sweep wings and 4 massive General Electric afterburning turbofans, but everything possible has been done to further improve its sleekly curved fuselage. It has advanced terrain-following radar for its low-level mission and a complex kit of electronic countermeasures equipment. The nose radome cavity and other parts of the fuselage were modified, while the use of radar-absorbent composite materials for many components and similar skinning and seals, particularly on the wings, helped reduce the radar cross-section to 1/10 that of the B-1A, or in other words, 1/100th that of the B-52. In fact, the B-1B has a smaller radar cross-section than many private light aircraft. The really major change between the two aircraft came in the design of the engine intakes. Since high-altitude dash speed was no longer required, the variable ramps could be dispensed with, the nacelles swept, the ducts curved and fitted with radar-absorbent baffles, and the whole intake lined with radar-absorbing composite material. The diagram clearly shows the differences which make the B-1B so much more stealthy than the old B-52, particularly in the use of curves instead of straight lines, and the reduction of the radar surface presented by the engines. All these features make the Lancer an invaluable part of Strategic Air Command. But even as the aircraft was entering service, work was well advanced on a brand new advanced technology stealth bomber. Inside a closely guarded building in Palmdale, the prototype of a revolutionary new airplane was taking shape. All the design was done on a three-dimensional graphics computer, and all production work is controlled by computers. In fact, you could say that the Northrop B-2 was designed by computer, built by computer, and is itself a flying computer. Everything about the B-2 is designed to render it invisible to radar, from the incredible wing leading edge to the painstakingly contoured engine intakes and cockpit canopy, which are a construction engineer's nightmare. Slightly darker areas on the undersurface conceal a high-resolution Hughes LPI radar, the initials standing for low probability of intercept, and meaning that even when the terrain following and target acquisition radars are switched on, they are very difficult for an enemy to detect. Bearing a superficial resemblance to Northrop flying wing projects 40 years ago, the B-2 actually shares the same wingspan of 172 feet, but there the similarity ends. Perhaps the single most unbelievable feature is that the wing leading edge curves round to the upper surface, but ends in a razor-sharp edge from which the lower surface follows a concave curve. Any aircraft designer will tell you that an aircraft can't fly with a wing like that. But, like the bumblebee, which is too ignorant to realize it can't fly with such tiny wings, the B-2 goes ahead and flies anyway. The B-2 is powered by 4 non-afterburning General Electric F-118 turbofans, with cunningly designed non-reflective intakes above the wing leading edge, curving back to curiously flattened exhaust nozzles above the trailing edge. These emit hardly any infrared, and at cruise altitudes are also very quiet, while special fuel additives eliminate contrails. Control in flight is achieved by large split surfaces at the wingtips called drag rudders, since the aircraft has no vertical surfaces to reflect radar waves. This diagram first shows a typical mission profile for an old B-52 Stratofortress. The circles show the distances at which overlapping AWACS, surveillance, and air defense radars can detect its approach to the target. Because of the B-52's high radar cross-section and other emissions, it can be detected early and is thus very vulnerable to countermeasures. On the other hand, because the Northrop B-2 has such a low RCS, reflecting less than 0.1% of its image back to an enemy radar, it can weave its way unseen through this minefield of detectors at either high or low level. The B-2 is the world's first aircraft to be built almost entirely from radar-absorbent composite materials, and while the jagged trailing edges might look odd, they are composed of straight lines, all aligned at one of 2 fixed angles. They thus shed radar reflections at angles away from the enemy transmitter. The same principles are employed in all hinged doors, such as on the landing gear. The fact that the B-2 is so virtually indetectable to radar poses problems for friendly air traffic controllers and other aircraft. When making an approach to a refueling tanker, for example, the aircraft therefore has to switch on an active radar transponder and extend special radar reflectors so that it can be seen. Of course, in broad daylight, this is no problem, but operationally, the B-2 will normally be flown at night. It is also said that the B-2's range is so great that in-flight refueling will not be needed during a bombing mission. A figure of 4,500 nautical miles has been given for its tactical radius, but it's impossible to verify this. During the landing approach, the B-2's drag rudders are all extended at 45 degrees, and the auxiliary intakes also open to further increase drag and supply extra air to the engines. Once the aircraft is touched down, on main landing gear similar to that of the Boeing 767, the drag rudders are open fully to slow it down. Due to enter service in 1992 or 93, the planned fleet of 132 Northrop B-2s will give Strategic Air Command a bomber at the forefront of military technology, which will remain in the front line for at least 3 decades. Another aircraft with a long lifespan is the fabulous Lockheed SR-71 Blackbird, which was finally retired from the front line in February 1990, after more than a quarter century of service. The Blackbird, so called because of its dull iron ball radar reflective paint finish, is to many enthusiasts the most spectacular aircraft ever to go into production. Developed from the A-12 as a strategic reconnaissance aircraft with the ability to fly at speeds in excess of Mach 3 at heights approaching 90,000 feet or 17 miles, the SR-71 is powered by 2 huge Pratt & Whitney J58 afterburning engines. These emit an enormous amount of heat, but the aircraft flies so high and fast that no missile has yet succeeded in shooting one down, despite the fact that the SR-71 has been used over many war zones. Another reason for its success is that the aircraft embodied what were for their time the ultimate in stealth features. The engine intakes had conical fronts, and the twin fins were canted to reduce radar reflectivity. Nothing could be done about the noise the Blackbird inevitably made, but a lot else could be achieved. In the Skunk Works factory, some of these other features become apparent. The airframe is built out of heat-resistant titanium alloy, and the sharp chine along the fuselage combines with wing and body blending to provide a relatively small radar cross-section. The leading edges of the tail fins were made with a zigzag structure which helped to reflect incoming radar waves away from the enemy transmitter. The same treatment was applied to the leading edges of the wings, and for the first time, extensive constructional use was made of radar-absorbent plastics and composite materials, although they were not load-bearing. The SR-71 has never been a stealth aircraft in the modern sense, and in fact, when it made its record-breaking transatlantic crossing to land at Farnborough in 1974, it was detected on ordinary radar at over 200 miles. But the Blackbird pioneered the way for many of the features which have emerged in different ways on the Northrop B-2 and Lockheed's own F-117 stealth fighter and attack aircraft. One of the SR-71's biggest shortcomings was the thirst of its huge engines, which meant that in-flight refueling from KC-135s was a necessity on many missions. Thus, even if the Blackbird itself had a small radar cross-section, enemy AWACS aircraft would be able to spot the tanker. For all its shortcomings in the modern aerial battlefield, the Blackbird remains to many people a striking symbol of what can be achieved if you try hard enough. Another aircraft about which much the same can be said, although it is totally different, is the Lockheed TR-1, latest variant of the large U-2 family, whose first prototype flew as long ago as 1955. Even though it predated the SR-71 by more than a decade, this aircraft is likely to remain in service for several more years, and it is interesting to look at why. Designed like the Blackbird to undertake reconnaissance missions at extremely high altitude, the U-2 family adopted a totally different approach. It only has a single engine and one pilot instead of 2, and is very quiet with a low infrared signature. With an incredibly long wingspan for its size of 103 feet, it looks more like a glider than a powered airplane. Those long wings actually serve two purposes. They enable the aircraft to cruise slowly in the very thin air at extreme altitude. They also resonate in the high-frequency radio band rather than in radar frequencies. The early grace of these high-flying birds has gone with the long nose and massive underwing pods, but those house some of the most sensitive surveillance equipment possible to imagine. This includes an advanced synthetic aperture radar system, which generates pictures as perfect as those from a radar some 30 or 40 times bigger. The only problem with the TR-1 is that the flexing in those long wings means that landing is very hairy and needs a commentator in a chase car to give the pilot an exact indication of where he is in relation to the runway. In complete contrast to most of the aircraft we have seen so far, except perhaps the B-52, is the McDonnell Douglas F-4 Phantom. Although for many years the attack fighter against which all others were judged, it incorporates no concessions to stealth at all, being big, incredibly noisy, belching smoke and radiant heat, and with huge angular engine intakes, which could almost have been designed to give the biggest possible radar cross-section. The Phantom is still a remarkably useful aircraft in both land-based and carrier-borne versions, and in the F-4G Wild Weasel version proved itself invaluable during the Gulf War in suppressing Iraqi radar installations. But it is now an old airplane, and in combat is usually accompanied today by at least one General Dynamics FA-16 Fighting Falcon. Although not itself a stealthy aircraft, the designers put some thought into making the F-16 at least partially invisible. For example, the cockpits are now coated with an extremely thin gold film, which helps reduce their radar reflectivity. Similarly, radar-absorbing material is used in the huge inlet duct for the massive afterburning turbofan engine. These features are claimed to reduce the radar cross-section by as much as 40%. Like all modern tactical combat aircraft, the F-16 could not survive against enemy heat-seeking missiles without the ability to eject flares. These brightly burning heat sources are designed to present a juicier target and lure infrared sensors away from the jet's tailpipe. Flares, as well as chaff or window, are controlled by the aircraft's own electronic warfare or passive air defense system. If this detects illumination by hostile radar, it automatically ejects chaff. If instead it detects an incoming heat-seeking missile, it throws out flares at intervals so close that the missile never gets a chance to lock onto the aircraft itself. Although not a stealth feature as such, the aircraft can also carry anti-radiation missiles to knock out enemy tracking or missile guidance installations on the ground. A new development which also uses speed and agility as its main defensive weapons, rather than relying upon stealth, is the experimental X-31, developed jointly by Rockwell in the United States and Messerschmitt-Bölkow-Blum in Germany. It's described as an EFM, or Enhanced Fighter Maneuverability Aircraft. Quite small, with a span of less than 24 feet, it's powered by an afterburning F404 engine, which must emit a lot of radiant heat. But in this case, that same heat is put to useful purpose. Around the tailpipe are three large flaps, or paddles, which can be deflected up to 10 degrees to give the pilot very powerful extra control over and above that provided by the ailerons and canard foreplanes. The X-31 is designed to show how to maneuver at below stalling angles of attack, which is exactly what the Russian Sukhoi 27 has been doing for years. Certainly, post-stall maneuvering was from the start a requirement for the most sophisticated aircraft in the Western world today, the fabulous ATFs, or Advanced Tactical Fighters. The first of these is the YF-22A, two prototypes of which have been produced by a partnership between Lockheed, General Dynamics, and Boeing. One has a pair of Pratt & Whitney F-119 engines, and the other General Electric F-120s. Both engines set totally new levels of thrust-to-weight ratio and enable the YF-22s to do things never before possible, such as cruising for as much as an hour at supersonic speed without using afterburners. These new engines give an unprecedented radius of action and long loiter time over the battlefield. Although the aircraft are not fitted with thrust reversers in order to save weight, they are equipped with afterburners, boosting thrust to something approaching 35,000 pounds per engine. For stealth reasons, the exhaust ducts are almost two-dimensional, giving a low infrared signature. In plan view, these nozzles are fan-shaped. Designed from the outset as a stealth aircraft, the YF-22's skin is without blemish, and moving parts such as the wheel doors are deliberately shaped to give no radar reflection at the edges when closed. In flight, the YF-22 is a beautiful aircraft with exceptionally clean lines when viewed from any angle, and not the slightest crack or discontinuity on its surface. Like all the new advanced tactical fighters, the aircraft is control configured, which means it is totally unstable and could not fly at all without fast-acting control computers which respond instantly to the pilot's wishes. These drive the leading edge flaps, outboard ailerons, inboard flaps, twin slanting rudders, and twin tailplanes inset into the very thin but sharply tapered wing. Notice also how all the leading and trailing edges follow parallels to reduce the radar cross-section. The high-mounted cockpit gives the pilot unsurpassed vision, and even its edges are specially shaped to prevent giving a radar return. Similarly, the engine intakes on either side of the diamond cross-section fuselage are designed both for perfect aerodynamic performance and to give a minimal radar cross-section. Most of the aircraft is constructed of thermoplastic composite materials, particularly the wing and fuselage, and extensive use has been made of radar-absorbent structure. The engines are close together for rapid roll, and the tail surfaces are enormous. Agility is further enhanced by the relatively short overall length, which is almost identical to the 63 feet 9 inches of the F-15 chase aircraft. A general opinion is that while Northrop have gone all out for stealth in their rival YF-23, the Lockheed consortium chose to try to build a better all-round fighter. And certainly if it came to a competition between the YF-22 and the F-15, there would be no real contest at all. Competition from the YF-23 will be an entirely different matter. Built by Northrop and McDonnell Douglas, the YF-23A is probably the more stealthy of the pair, especially from the front. One of the most obvious differences between the aircraft is that Northrop have succeeded in using only 2 tail surfaces in so-called butterfly configuration instead of 4. The YF-23 uses the same engines as the YF-22, the Pratt & Whitney version on the first prototype and General Electric's on the second. Both engines give performance like nothing seen before, especially at the light weights of the prototypes. Pulling into a vertical climb from liftoff, the 23 could carry on going upwards like a space shuttle to about 100,000 feet, the wings being really unnecessary. Both of the advanced tactical fighters share common features, particularly in general wing shape and the use of parallel edges. In order to achieve a better stealth profile, though, Northrop have flattened the fuselage and pushed the engines apart, making the 23 some 6 feet longer than the 22, in order to keep the weight and load-carrying parameters roughly the same. The aircraft maneuvers using the 2 large tail surfaces, which Northrop call ruddervators. These can work in unison or in opposition to control pitch and yaw. This arrangement obviously gives a lower radar signature than the more conventional one on the 22. One surprise to many people is that neither aircraft has canard foreplanes, which were heavily featured in early artists' impressions. The Northrop aircraft has unique underwing engine intakes, from which ducts curve upwards and inwards to meet the engines. This system removes the problem of enemy radar seeing the front of the engines, which was one of the major defects of the old B-52 and F-4. Both aircraft have similar internal weapons bays, but the 23 can carry AIM-120 advanced medium-range air-to-air missiles in tandem with AIM-9 sidewinders because of its extra length. The 22 carries sidewinders in extra compartments along the fuselage instead. Another minor difference is that the YF-23's refueling receptacle is in the center of the fuselage, while the 22's is on the left. No reliable figures for either aircraft's range have been released, but they are likely to be in a different magnitude to those for any earlier machine of comparable size, weight, and performance. Here we see the 2 YF-23 prototypes flying together, the first with Pratt & Whitney engines being painted slightly darker. Both demonstrate the superb flying precision afforded by the computerized control system. Even during in-flight refueling, the 2 aircraft are as synchronized as if they were stuck together with glue. In this sort of view, one more significant difference between the Northrop YF-23 and the Lockheed YF-22 can be seen, and that is the canopy design. Here, the 22 is actually more stealthy because the 23 has a separate metal-framed windscreen which must be highly reflective to radar. Another interesting feature is that the 23 produces a highly visible vortex trail from one wing during hard rolls. Pilots who have flown the Northrop YF-23A describe it as one of the easiest aircraft to fly ever built, the most user-friendly in computer jargon. Indeed, it's said that all a pilot needs to be told on his first flight is the takeoff and landing speed, and the airplane will do everything else for him. But comparisons are invidious, and whether the 22 or the 23 is selected for service, either will be loved by the men who are privileged to fly them. An even more futuristic design than either of the advanced tactical fighters now flying would have been the U.S. Navy's equivalent. The A-12 Avenger attack aircraft was developed in even greater secrecy than the others and would have replaced the venerable A-6 Intruder in the carrier-based attack squadrons. It was a pure flying wing, sharing similarities with the Northrop B-2, but with many differences. It would have been a perfect stealth aircraft, with the lowest radar signature of all, and the Air Force was also keenly interested in it as a possible replacement for the F-111. Unfortunately, escalating costs resulted in its eventual cancellation in January 1991, and all we are left with are the artist's impressions and models. These are still vivid and show what might have been. The Nighthawk is the first true stealth airplane in operational service and is actually a precision ground attack machine rather than a fighter, despite its Air Force designation of F-117. The typical military terminology, which delights in obfuscation, a word meaning darkening or hiding, uses the phrase low observability in describing the Nighthawk rather than stealth, which suggests creeping around in people's backyards. But that's what stealth is all about, however you mince words. Getting into your target undetected, destroying it, and getting away again unseen. That's what the F-117 is designed to do, and demonstrated its ability to do time and time again in the Gulf War against Iraq. Like the SR-71 and U-2, it was designed and created in absolute secrecy at Lockheed Skunk Works. And even though the first of 59 for the U.S. Air Force flew in June 1981, its shape was only revealed to the general public in a deliberately retouched photograph some 8 years later. That shape is something else and is determined by a different approach to stealth technology than those broadly seen already. You can immediately see that the aircraft is full of sharp angles and pointed shapes, not rounded like the B-2 or contoured like the YF-22 and 23. That's because Lockheed came up with a concept known as faceting. The entire external surface of the F-117 is made up of flat facets, rather like a cut gemstone, which do not absorb radar energy, but instead radiate it out in so many directions that there is hardly any return signal. Of course, a sharp-edged pyramid shape is hardly ideal in the aerodynamic sense, and like the B-2s and YF-22s and 3s, the Nighthawk is so inherently unstable in flight that it can only be flown by its onboard computers. The pilot points it, the electronic brains do the rest of the work. The wing profile is necessarily inefficient, and it's amazing to see the Nighthawk soar like a bird of prey, as it appears to be from so many angles. The straight lines, always following parallels, the beak nose, and even the pair of tail feathers, which are in fact pivoting rudder vaders, similar to those on the YF-23, perfect the image. The F-117 is a bird of prey and of stealth, as reflected in its name. Pilots claim its maneuverability to be superb, despite that weird shape, which conceals two General Electric F404 turbofans. Housed in large boxes either side of the fuselage, they have inlets covered by fine gauze mesh. Everything has been done to either absorb radar waves or reflect them away from the enemy transmitter, so he has no idea this new Blackbird is in his skies. Sometimes it seems to float in the air, rather more like a lazy pike in a pond than a bird far above, and again the analogy is apt. Fish need to keep at the right temperature, and so does the F-117, with the engine cooled by secondary airflows, and any hot parts screened by the lower lips of the exhaust nozzles being extended and curved upwards. The F-117, like other stealth aircraft, has a range and endurance which are still classified, but known to be enormous. It has two 11,000-pound turbofans, which need a lot of juice, so it has a receptacle for in-flight refueling. Special retractable radar reflectors help it to mate with its milch cow, especially at night when it is most at home. To begin with, F-117s were only allowed to fly at night, to preserve secrecy. So the very fast landing approach, another penalty of the wing design, was not apparent until later. A drag chute is essential, and the circular canopy streamed is usually black to match the aircraft's iron ball paint finish. The whole aircraft is made of either composite or radar-absorbent structural materials, the first phase referring to its skin and the second to its guts. On the landing approach, another feature of engine design is apparent. From the front, there is a high-pitched whine, while from the rear, there is only a faint rumble. That is enough to keep an enemy confused, especially when he can't see an airplane on his radar at all. F-117 Nighthawks first went into action during the Panama Crisis in December 1989, a fact only revealed after the event. Much more significant has been their deployment and performance during the United Nations campaign to liberate Kuwait from Iraq. Here, F-117s demonstrated their superb capability of getting into and out of a target zone without interception by bringing back video evidence of missions against precision high-value targets. Such as the Ministry of Defense in Baghdad on the opening night of the shooting war. In view of the modern electronic battlefield, it may be fair to claim that only a stealthy aircraft could have been expected to do this and bring back the evidence. The sure thing is, stealth is here and here to stay.